Welcome students to the next session in electrochemistry. In this session, I will be explaining to you the quantitative aspects of electrolysis. Electrolysis has wide applications. As you know, electrolytic refining, we can say one electrolytic refining of elements like copper, refining of metals like copper. Secondly, electroplating. It has very wide application in industry, electroplating. Thirdly, we can say electrometallurgy. Especially the alkaline and alkaline earth metals can be obtained only by electrolytic reduction. That is what we mean to say electrometallurgy. In all these processes, we pass electricity through solutions and substances are discharged at the electrodes. The quantity of electricity that is passed is measurable because when you pass 1 ampere current for 1 second, you know you are passing 1 coulomb of charge. So I into T in seconds gives you the charge in terms of coulombs. So that is measurable. Again, the substances that are discharged at the electrodes can also be measured. If it is a gas, we can measure the volume of the gas, and from the volume and pressure and temperature we can calculate the mass of the gas. If these are substances deposited, then whatever material is used as the electrode, we can weigh it before and after the electrolysis and we can obtain the mass. And there are quantitative relationships between the quantity of electricity passed and the amount of substances discharged. This was the field in which Michael Faraday did exhaustive research, and he put forth his findings in the form of two laws which go by the name of Faraday's laws of electrolysis. Very simple to understand, at the same time very valuable laws with regard to electrolysis. The first one says that the mass of a substance liberated, at an electrode is directly proportional to the quantity of electricity passed through the electrolyte. Through the solution. So I can write the mass of the substance deposited is directly proportional to the quantity of electricity Q. This can be written as M proportional to I ampere into T seconds. And the proportionality constant, I will give it as Z I into T, where this Z is called electrochemical equivalent. When I is equal to 1 ampere and T is 1 second, Z becomes equal to M. So the electrochemical equivalent is the mass of this substance that would be deposited when you pass 1 ampere current for 1 second. The second law of Faraday is when the same quantity of electricity is passed through different solutions, the amount of substances liberated at the electrodes are directly proportional to their chemical equivalents. What is chemical equivalent? For an element, chemical equivalent or equivalent mass, equivalent is equal to its atomic mass by the charge on its ion. For example, for sodium, the charge is 1. So, atomic mass itself will be equivalent to its chemical equivalent. If you take an element like magnesium, chemical equivalent of magnesium, I would write here, chemical equivalent of magnesium would be atomic mass of magnesium by the charge on its ion. We know it is 2. Let us try to explain it this way. Supposing I take fused sodium chloride and electrolyze it. Then the sodium ion will migrate to the cathode, and to get deposited or discharged as sodium atom, it would need 1 electron, isn't it? Now I need 6.023 into 10 to the power 23 sodium ions. They move to the cathode and they get discharged as 6.023 into 10 to the power 23 atoms of sodium. It needs obviously the same number, 6.023 into 10 to the power 23 electrons. Or I can write 1 mole of electrons. You know this number is Na, Avogadro number, which stands for Na. Here it stands for 1 mole of electron. You know the charge on 1 electron is 1.6021 into 10 to the power minus 19 coulomb. That is the charge on an electron. So 6.023 into 10 to the power 23 multiplied this charge will give you the quantity of electricity Q, which will be needed to discharge 6.023 into 10 to the power 23 atoms of sodium, in other words, which is 1 mole of sodium. 1 gram atomic weight or 1 mole of sodium needs this many coulombs. This Q is, if you multiply, you will find it to be 96,487 coulombs. This quantity is called 1 Faraday to honor the scientist who has done exhaustive work in this field. So when we say we passed 1 Faraday current, we mean to say we have passed 96,487 coulombs, or we can say we have passed 1 mole of electrons, and 1 mole of electrons will bring about the deposition of 1 mole of a univalent element, isn't it? So 1 Faraday current, 1 Faraday is equivalent to 96,487 coulombs, which is equivalent to passing 1 mole of electrons, which will bring about the deposition of 1 mole of univalent element, or I can say 1 gram equivalent, 1 chemical equivalent of an element. 1 chemical equivalent of an element. Let us consider the other ions now. If we consider electrolyzing magnesium chloride, the magnesium ion will go to the cathode and will get discharged as magnesium atom, and it will need 2 electrons. Then 6.023 into 10 to the power 23 Mg2 plus ions will get discharged as the same number of magnesium atoms, and this will be needing the same number of 2 into, that is the main thing here, 2 into 6.023 into 10 to the power 23 electrons. That is the main thing to be considered here. See, let me repeat. 6.023 into 10 to the power 23 magnesium ions will be discharged as 6.023 into 10 to the power 23 magnesium atoms at the cathode, and that would be needing 2 electrons. For neutralizing one charge, you need 1 electron. For neutralizing 2 positive charges on each magnesium ion, you need 2 electrons. So 2 into 6.023 into 10 to the power 23 electrons. Now this you know is 1 mole of magnesium. 1 mole of magnesium, and this in terms of charge would be 2 into 6.023 into the charge of an electron, 1.6021 into 10 to the power minus 19 coulomb, and so these two together, the value we already saw is 96,487 coulombs or 1 Faraday. 1 Faraday, and so we need 2 Faradays. And aluminium, for the along the same principle, we can say aluminium ion, a trivalent aluminium ion, to be discharged at the electrode as aluminium atom will be needing 3 electrons. And so 1 mole, I will write it here as 1 mole of aluminium ion. You know that 1 mole is 6.023 into 10 to the power 23 aluminium ions, or Avogadro number of aluminium ions. To be discharged as 1 mole of aluminium atoms, it will be needing 3 moles. Here 3 moles of electrons. 3 moles of electrons, and that will be equal to 3 into Avogadro number of electrons multiplied by the charge 1.6021 into 10 to the power minus 19 coulomb. This will be the quantity of electricity, which will be equal to 3 Faraday. So let us sum it up. So 1 mole of sodium ion to be discharged, we need 1 Faraday of electricity. This is the quantity of electricity. Then to discharge 1 mole of magnesium ion, we need 2 Faraday. We saw here already, we need 2 Faraday. And 1 mole of aluminium ion, we need 3 Faraday, isn't it? So these are all moles. Here I will remember, this one is number of mole. Number of mole. 1 mole of these things, each ion requires, I can say NF coulombs. NF coulombs of charge or electricity. Or if I take 1 Faraday, the same quantity, to interpret the second law, 1 Faraday of electricity if I take, I will be getting 1 mole of sodium. 1 mole of sodium, I will be getting, it needs 1 mole of magnesium needs 2 Faraday, isn't it? So I will be getting half mole of magnesium, or 1/3 mole of aluminium, and this is nothing but 1 chemical equivalent of equivalent mass of 1 equivalent mass of sodium, 1 equivalent mass of magnesium, 1 equivalent mass of aluminium. This is the second law of thermodynamics, that is, by passing the same quantity of electricity, say 1 Faraday, we discharge 1 equivalent mass of any material at the electrode. I am going to represent the facts that you learned so far in a slightly different way. I will write here 1 Faraday. One Faraday is quantity of electricity. This can be converted into coulombs. When I say 1 Faraday, you know you will be able to say it in terms of coulombs. For that you will multiply it by 96,487. Number of Faradays you multiply by 96,400, you will get the number of coulombs. Number of coulombs is related to the I in amperes and time in seconds. So this is given by the product of I into T. So it is both ways. If you are given I and T, you can calculate the coulombs, or if you know the number of coulombs of charge, if amperage is given, you can calculate the time, or if the time is given, you can find out I. Now 1 Faraday, you know, is 6.023 into 10 to the power 23 electrons. Electrons are, it is equal to 1.6021 into 10 to the power minus 19 coulombs. So 1 Faraday stands for this. And from C, we can calculate the number of electrons by multiplying by the relationship, that number of electrons into 1.6021 into 10 to the power minus 19 C. So if you know the coulombs of charge, if you are asked how many electrons are passed, you can divide by the charge of an electron to get the number of electrons. Now 1 Faraday current, you know, is going to discharge 1 gram equivalent. Gram equivalent of any substance. Now how do you get mole from this? Multiply by N, that will give you 1 mole. Mole or gram atomic weight or gram molecular weight. Gram equivalent multiplied by N gives you mole or gram molecular weight. And once you know the number of moles, you can get the weight in mass, weight in grams, by multiplying by the atomic or molecular mass. So this way when we write, it is into, multiply into. Here also it is into. Okay. Now 1 Faraday, the number of Faradays is connected to mole, because N of Faradays will give you 1 mole of whatever substance you are, that is going to be discharged at the electrode. Or if you know the number of moles, you can also calculate the number of Faradays required to discharge. So all these quantities are interconnected, and once you know the relationships between them properly, you will be able to work out problems easily. So we will work out the problems to understand these relationships. Let me tell you once again. Here I have started with 1 Faraday that I have written in the middle. When I say 1 Faraday, I mean the charge in coulombs. For that, this is coulombs. I multiply that by 96,487 coulombs. Number of Faradays can be multiplied, or if you know the coulombs, you can divide by this to get the Faraday. So remember, it is, what I mean is into. I have put into sign here. And then once you know the number of coulombs as the product of I ampere and T second, these relationships, using this relationship we can calculate whatever we require from the given data. If you know the charge, you can calculate how long the time, how long a current of a certain ampere is passed. Or if you are given the current strength in amperes and time, for how long it was passed, you can calculate coulombs from the coulombs you can calculate the number of Faradays, and from the number of Faradays you can calculate how many moles of the substance is deposited, and from the number of moles, if you are required to get the weight in mass, you can calculate the weight of the substance that is discharged. And you know, 1 Faraday is equivalent to passing 1 mole of electrons, and each electron carries 1.6021 into 10 to the power minus 19 coulomb. So multiplied by this Avogadro number, it gives you the the charge of the quantity of electricity in terms of Faradays, that is 96,487 coulombs. And once the number of coulombs are known, you can calculate how many electrons have been passed. That is, you divide the number of coulombs by the charge of an electron, that will tell you the number of electrons that has passed through the solution. Now it's time for problems. Read the first problem. If a current of 1 ampere flows through a wire for 3 hours, how many electrons flow through it? Note down the data given. You are given the value of I and time. So we can calculate Q straight away. Q is equal to I into T. Substitute the values. 1 ampere into 3 into 3600 seconds. So this gives you a value of 10800 coulombs. Right. Now what relationship do you need to solve the problem? You have calculated the charge that has passed through the wire as so many coulombs. You know the charge carried by a single electron, and you are required to find out how many electrons flow through. So obviously the number of electrons can be calculated by dividing this charge that has passed through the wire by the charge of an electron, which is 1.6021 into 10 to the power minus 19. Both are in coulombs. So that will straight away give you the number of electrons, which is 6.75 into 10 to the power 22. The other relationship that you can use here is when you pass 96,487 coulombs, or you can roughly take 96,500 coulombs, that is equivalent to passing Avogadro number of electrons, 6.023 into 10 to the power 23 electrons. So when you pass this 10,800 coulombs, that is equivalent to passing how many electrons. So the ratio would be, let it be x. The x can be found out by 10,800 by 96,487 into. So this will give you, on solving, the same value that you have got by the other method. I suppose it is clear. Read the second problem and write down the data. Think of a suitable relationship to solve the problem. Have you calculated the value of Q here? Q is equal to I into T. The value of I given here is 50 milliamperes. How would you substitute that? 50 into 10 to the power minus 3 ampere. That is 50 milliampere, and then time is 60 minutes. So 60 into 60 seconds. This is giving you a value of 180 coulombs. I suppose you got the value. Then you have to think of the relationship between the charge to be passed and the mass of copper deposited. If you pass 2 Faraday current, because it's a divalent, copper ion is divalent, 2 into 96,500 coulombs of charge, if you pass, that would be depositing 1 gram atom of copper, which is 63.5 grams. Therefore, for 180 coulombs, what is the mass of copper that you would be getting? So, if you take it as x, the ratio will be x by 63.5 equal to 180 by, so can 63.5. When you solve for x, here you get a value of 0.059 gram. So, two simple problems must have made these concepts clear to you. In the third problem, you are asked to calculate the charge required for a few reductions and oxidations. We will take up one by one, and I will teach you how to do that. In the first one, it is only reduction of SN4 plus to SN2 plus. So, SN4, that is simple enough. You know, to reduce 1 mole of SN4 plus to SN2 plus, you will be requiring 2 moles of electrons. In other words, 2 Faraday current. So, straight away I will write for the first one SN4 plus to SN2 plus 2 Faraday. So, that is equal to 2 into 96,500 coulombs. If you are asked to calculate the charge, you have to give the answer in coulombs, not in Faraday. In the second one, 1 mole of MnO4 minus is to be reduced to Mn2 plus. Look at it and find out which element undergoes reduction. It is Mn. But Mn is present as MnO4 minus. So, you have to calculate the oxidation number or oxidation state of Mn in MnO4 minus. So, I will write MnO4 minus. I will write the oxidation state straight away, because calculation of oxidation number I don't have to teach you now, all of you must be knowing. So, we have to consider it as only a reduction of Mn from plus 7 state to plus 2 state. So, this requires 5 Faraday of charge, or 5 into 96,500 coulombs. Third one is also similar, but there is a slight change. Here, reduction of 1 mole of Cr2O7 2 minus, Cr2O7 2 minus, that is the dichromate ion, to Cr3 plus. So, as I told you, we have to calculate the oxidation state of chromium in this. This you can find it to be 6 plus 6. So, plus 6 to plus 3. But don't be in a hurry to say immediately 3 moles of electrons. Here there are 2 chromium atoms in dichromate ion or Cr2O7 2 minus ion. Both the chromium atoms are to be reduced from plus 6 to plus 3. Because 1 mole of dichromate ion itself has 2 chromium atoms, naturally both are to be reduced, we cannot separate them. So, we have to calculate taking into account both the chromium atoms. So, for 1 chromium atom it is plus 6 to plus 3, that is 3 moles. For 2 chromium atoms it will be 6 Faradays. 6 Faradays, so 6 into 96,500 coulombs. Fourth one involves the oxidation of 1 mole of FeO to Fe2O3. FeO is ferrous oxide, in which iron is in the plus 2 oxidation state. When it is oxidized, it forms ferric oxide, where iron is in plus 3 state. So, it is only 1 mole of FeO, which contains only 1 iron atom. So, it is only 1 Faraday. Fe2 plus to Fe3 plus. Here it may be two iron atoms present, but we are only concerned with oxidation of 1 mole of FeO. So whatever may be the number of moles of Fe2O3 that you get, for oxidation of 1 mole of FeO, you consider only one atom of Fe which is in plus 2 state. So we can state the answer to be 1 Faraday or 96,500 coulombs of charge. The last one is oxidation of 1 mole of water. By now I suppose you are all clear as to how to do this problem. So should be able to calculate the oxidation number of oxygen in water, which is -2, and in O2 it is 0. So it is adding 2 moles of electrons to water to make it oxygen. So 2 moles of electrons per mole of H2O, it will be 2 Faraday. This is one important type of problem in Faraday's laws. So I suppose you have understood that. Now read the fourth and the final problem of this session. You are given 3 cells A, B, C containing solutions of zinc sulfate, silver nitrate and copper sulfate connected in series, and a current of 1.5 ampere is passed through these electrolytes, but for how long it's not given. But you are told that the current is passed for such a time, such a duration till 1.45 gram of silver is deposited in cell B, and you are asked to find out what is the duration for which the current is passed and what masses of zinc and copper are discharged. Only the problem looks long, it's not difficult. You know, if you are given the value of I and T, values of I and T, you can calculate Q, the quantity of charge, but the time data is not available. But we have a relationship between the mass of silver deposited and the quantity of charge that is required to deposit that. You know that, isn't it? What is that? Ag is a univalent ion. Ag plus is a univalent ion. So to deposit 108 grams of silver, you require 96,500 coulombs or 1 Faraday, isn't it? Coulombs of charge. You have got 1.45 grams of silver. So what is the charge that has passed through? It can be calculated. So the value of X can be found out as 1.45 by 108 into 96,500. So this can be calculated. Do it and then check with the value. Once you know the charge, it is very simple to calculate. T I into T is equal to, here I is 1.5 ampere into T to be found out is equal to 1295.6 coulombs. Calculate the value of time. For the rest of the problem, I will be giving you only the answers, not the solution by steps. I am going to give you only the answers. I will just explain how to do the second step, that is calculation of the amount of zinc. See, you have passed the same current, that is 1295.6 coulombs of charge only, through all the solutions. So for zinc also the same amount of charge only is to be taken into account. The relationship between the mass of zinc and the charge is for for discharging 1 mole of zinc, that is 65.3 grams of zinc, you require 2 Faraday. Okay, 2 into 96,500 coulombs, and you have passed 1295.6 coulombs of charge. So what is the amount of zinc that can be deposited for that quantity of electricity? That is a relationship that you have to write as you have written in the case of silver, and you can calculate in a very similar way. You can calculate the mass of copper that is to be deposited. Hence I am going to give you only the answers for the other parts of the problem, and I suppose you will do it by yourself and check with the answers. Thank you.